Um, Thanks a lot for the introduction. Thanks a lot for organizing all of this. It's been a lot of fun so far. I'm very happy to talk about this work because I was very excited about it, and it's actually it's not a lot of work, so it's also nice to present. I can actually take my time and go over the details of what we did and what it implies and so on. So yeah, it shouldn't be too hard on you either, hopefully. Good. So the talk is titled Directed ST Connectivity with Few Paths is in Quantum Log Space. So for now, what you want to take away is there's quantum log space, and then there's this sort of canonical problem of directed ST connectivity. And so essentially what we do is we show that for this canonical problem, there actually seems to be a quantum advantage. Like we can solve certain problems that seem hard to solve in classical log space. Okay? But before we go into the details of that, let's introduce log space, and there's different ways of doing it. Somehow it turns out that Turing machines are kind of helpful here, so I'm going to use that. So we start with L, or deterministic log space, where you imagine that we have a polynomially sized input tape, right, containing our input. And then we have this work tape, and we have an output tape. So it's very similar to the usual Turing machine setup, except that now we're restricting our work tape to only use order log n space. Okay? So again, our input is poly-sized, so we can read that off. We can spend a lot of time doing that, actually. But we can only sort of store or store log n sort of intermediate computations or bits. Okay, the output could be a 0 or 1 bit if it's a decision problem, but it could also be a polynomial length output, right? Because I can just sort of spend poly time to write my output on that output tape. So there's no problem there. So that's deterministic log space. Making this a little bit more interesting is a non-deterministic log space where, again, there's sort of different ways of looking at it, but one useful way is that you imagine there's a fourth tape here that contains a certificate. Okay, and so we sort of want to, in log space, verify that a certain property of the input holds, and we're given this certificate to help us in verifying that. Okay. A different variation on L is BPL, where this fourth tape now is a tape of random coins. Okay, it contains random bits, and our algorithm can read random bits off of that tape, and that should, help with our computation. And then finally, since this is a quantum conference, so BQL, or bounded error quantum log space, here we imagine, again, there's different ways of thinking about it, but one is where you imagine that you sort of have this extra tape with log n qubits now, and we can apply Hadamard gates, T gates, sort of universal gates that we can do measurements on these. So there's a lot of subtleties involved in how precisely, do we allow these measurements or not, and so on, but I prefer not to go into these at this point. So that's the setup, okay? So given this setup, we can prove a couple of easy things. One is that clearly L is sort of the most basic here. L is in NL, L is in BPL, because we're giving more power in the case of NL and BPL its term is in BQL, because we can just sort of put these qubits in plus state and measure them and get random bits. Okay? More non-trivial is the following result, that is that NL is in L squared, where L squared is the same setup, except that you're allowed to use log squared many bits of memory. Okay? So this was a very surprising result in that it seems that as soon as you sort of allow log squared space, then we can solve all the other problems here. Okay, so NL is in L squared. This was proven by Savage in the 70s. A different non-trivial result is that BQL is in L squared, which was proven by Watrous in 99. Okay, so these are sort of the diagram you want to keep in mind. Let's talk about problems that we can solve in these different models. Okay, and when we leave BQL out of this picture for a second, we talk about L, NL, L squared, BPL, then a very typical way of approaching these complexity classes or characterizing them is through ST connectivity. Okay, so for STCon, you imagine that there's some directed graph written on the input tape, There's some vertex S, some vertex T, and we're asked the question whether S is connected to T in this directed graph, okay? So if we don't have any space restriction, what will we do? We just do some sort of breadth first search, depth first search, and we can solve this problem. Right? We can solve this problem in polynomial time, okay? But if we restrict the space to be only of size log n bits, then this becomes pretty hard, okay? In fact, this problem becomes NL complete. So the fact that it is in NL just follows from the fact that your certificate could describe a path from S to T. The fact that it's NL hard comes from using a interpretation of Turing machines through their configuration graphs and thinking about S as the input state and T as an accepting state. Okay? Good. So that's ST connectivity on a directed graph. You can make this problem at least seemingly simpler by considering an undirected graph. Okay? So now on the input, taper again, given a graph, but now this graph is an undirected graph. And again, we want to decide whether S is connected to T. Now this problem, all of a sudden, is still L hard. So it still characterizes at least as hard as L, again, through some configuration graph argument. But more interestingly, this problem is in BPL. Okay? So it's in bounded error probabilistic log space, and the idea here is really essential, and maybe I also want to give this as a takeaway. This was also how I got interested in log space computation. So I like graphs, I like random walk algorithms, and also quantum versions of that. And these seem very closely tied to these log space complexity classes. Okay? So we've seen already this sort of NL complete STCon problem. Now for USTCon, this is L hard. And it's in BPL because you can run the following simple algorithm, which is just run a random walk starting at S. Okay? So you can do that because the identifier of a vertex will just be log n bits, so you can implement this random walk. You can pick a random neighbor, jump to that, and so on. And the fact is that on undirected graphs, random walks behave very well. So they mix fast, meaning that in polynomial time, they'll be able to reach any vertex with good probability. Okay, and so in particular, we should be able to reach vertex T and then decide that S and T are effectively connected. If we haven't seen T, then we decide that it's not connected. Okay, so it's quite natural for this class BPL. So putting it in BPL wasn't too much of an effort. A much deeper work, though, by Reingold showed that actually you can even put it inside L. Okay, so you can de-randomize this random walk construction. This used a lot of advanced tools based on expander constructions and so on, showing that in log space you can sort of create expander versions. You can blow up your graph into an expander. And for expanders, we already knew that you could solve this in L. Okay, so Reingold put this problem in L. Good, so we talked about L, NL, BPL, L squared. Now there's also BQL, right? So what can we say about BQL? So here we make a little bit of a style switch, because now we're going to turn to algebraic problems, okay? Because a lot of sort of quantum problems are naturally characterized, at least that's how we do it, characterize them by algebraic problems, okay? In particular, there's this problem called polyconditioned matrix inversion, which looks like this. So now on our input tape, we're given some matrix A, an n by n matrix, and we're promised that this matrix is polyconditioned. So you can imagine that means that the operator norm of A and the operator norm of the inverse of A are polybounded. Okay? And the task now is to return the inverse of this matrix up to additive inverse polynomial precision. Okay, so you can imagine we fix a vertex, we fix an entry I and j, and we want to return this entry. But as I explained, you can also just imagine writing out the full A inverse approximation on the output tape. Okay, so this is a problem that should ring a bell if you're sort of familiar with quantum algorithms, because this is a problem that we sort of know how to solve. And this is what Tashma did in 13. So it required some sort of tricks and tweaks to make it work, but you can effectively run HHL, so the quantum linear system solving algorithm, in log space. Okay. So an important point here is that when you usually think about HHL, we're going to think about using n qubits, but matrices of size 2 to the n, and polyconditioned means that these norms are bounded by polylog n, okay? So in the log space setting, polyconditioned means that these norms are bounded by a poly in the size of the matrix, okay? So that already should sort of tell you that we get this kind of new algorithm. We can try to do different things than we can do with HHL. And that's effectively what we do. In 16, Pfefferman and Lin also showed that, in fact, this problem is also BQL hard. Okay, so you get this nice BQL characterization through an algebraic problem. But of course, the title has connectivity, like L, NL, BPL squared. All these classes are sort of, a lot of research on them is sort of motivated and is driven by thinking about graphs and random walks and so on. So we really wanted to think about if there is some sort of graph problem that we can associate to BQL, is there some graph problem that we can solve with BQL rather than thinking about these algebraic problems. Okay, so more precisely, there's this motivating question, like can we find a quantum advantage in BQL over BPL for solving ST connectivity? Okay, the sort of canonical problem in log space complexity. And it seems that nothing was really known about that. So what we prove is that a restricted version of STCon is in BQL. Okay, so ST connectivity on directed graphs that satisfy a certain promise, we show how to solve these in BQL. Okay, so then you could of course ask, yeah, okay, but if you're putting some restriction, then maybe we can also solve these classically. Maybe we can also solve these in BPL. Okay, because let's say here the goal is really to maybe distinguish BQL from BPL. Okay, so the good news is that actually, if you manage to put this precise problem that we solve in BQL, if you manage to put it in BPL, you get $1,000. So they're not my $1,000. I'll explain you whose they are by the end of the talk. And the second point is that based on this algorithm, we're actually able to find a language that seems to separate BQL from L. Okay, so it's a language that seems to be hard for log space, but easy for bounded error quantum log space. And now again, you can ask, okay, what about polyconditioned matrix inversion? So I'll explain why that doesn't quite qualify here when we get to that. But for starters, so let's look at random walks on directed graphs and see where the sort of difficulties arise when you want to do random walks on directed graphs. So on undirected graphs, a quantity known as the hitting time is order n cubed, right? So from any vertex, you can hit any other vertex in expected time order n cubed. So that means, in particular, that also the random walk matrix P, which you can associate to a random walk on this graph, is going to be well conditioned, okay? And again, this poly in the size of the state space is what we call well conditioned now, okay? And that implies, for instance, that we can use polyconditioned matrix inversion to solve this problem in BQL. Okay, that's not very interesting because you can already solve it in L, in fact, but still. Then turning to directed graphs, consider, for instance, the following graph where you have this sort of directed path from S to T, and every vertex has a dangling edge to a sink beneath it, right? So what will a random walk do? It'll jump to the left, maybe, but with probability 1/2, it'll jump into that sink, and then it's done. So the probability that you will actually ever hit T before getting stuck in a sink is going to be exponentially small. This is a huge difference with what happens in undirected graphs. So effectively, the hitting time can be exponential, or I guess it could be even infinite, depending on how you define it. So that's a big difference, and this also reflects in the linear algebra. Okay, so if you look at the random walk matrix P, then it can be ill-conditioned in contrast to the undirected setting. And hence, we cannot use polyconditioned matrix inversion in BQL. Okay, so that would have been like the first idea that we try. Unfortunately, that doesn't work. Luckily, we found this sort of other idea that does work. So let Nij denote the number of paths between vertex I and j in the input graph. Okay, I'm going to assume that this graph is acyclic, so that this number of paths is finite between any pair of vertices S and T. Actually, you can assume that without loss of generality. So if Nij is the number of paths, and we're promised that the number of paths between any pair of vertices I and j is polynomial, so it's bounded by a polynomial, then we can return not just whether S and T are connected, we can actually return the number of paths from S to T in BQL. Okay, so we give a BQL algorithm that solves SD connectivity and even solves a harder problem on these graphs. They're called strongly few graphs. Okay, so these graphs have been studied. And the proof is actually simple, so that's the nice thing. So again, we're going to assume that G is a DAG, so a directed acyclic graph. So there's a log space construction that allows you to turn any graph into a DAG and solve that problem. So we can assume that without loss of generality. And then we're going to consider something that's slightly odd. So when you think about graph Laplacians, you think about the degree matrix minus the adjacency matrix, or identity minus the rescaled adjacency matrix. So what we consider is identity minus A as our Laplacian. We call it a counting Laplacian. So consider this matrix. So why do we call it a counting Laplacian? Because its inverse can be written as follows. So we're assuming that a to the n is 0, right? G is a DAG, so there cannot be a path of length n. So a to the n is 0. And then by using a Neumann series, you can rewrite this inverse simply as identity plus a plus and so on until a to the n minus 1. Okay? But that implies that taking any ij entry of this L inverse just gives us the number of paths from I to j, right? Because the ij entry of any power of a would give you, let's say of a to the k, would give you the number of length k paths, and we're summing over all possible lengths. Okay. So that's how you call this the counting Laplacian. Taking its inverse gives you the path count. Furthermore, the operator norm of L can easily be bounded by n, using this max norm inequality. And what's more interesting is that the operator norm of the inverse of L can be bounded by the max norm of the inverse, which is just characterized by this path count, right? So we're seeing that sort of the algebra, the algebraic properties here are characterized by these combinatorial path counting arguments. So in particular, we see that L is going to be polyconditioned, this counting Laplacian is going to be polyconditioned, if and only if the number of paths between any pair of vertices is polybounded. And that solves this problem, right? Because then that means that we can just solve a polyconditioned matrix inversion on that matrix L. And that allows us to output an estimate of this inverse. But since we know that this inverse is going to be integer valued, we can actually round it and return the exact number. Okay? This fact that we can round and return an exact number is a bit special in the quantum setting. Because a lot of quantum advantages that we know don't have that property. This brings me to the following point. So from this algorithm, we can prove the following corollary, which is that the language STCon SF, so SF stands for strongly few, so it's essentially graphs satisfying this. The language of all graphs that satisfy this condition and in which S and T are connected, this set of languages is in BQL. Okay? But this is a language. Okay, so there's no promise on the input because we effectively show on top of this algorithm that we can check that promise efficiently. So that puts a language in BQL, which seems to be hard classically. Okay, so this is the first, it's a non-promise language in BQL that's not known to be in BPL or in L. For comparison, there's other well-known problems which seem to separate BQL from BPL, like polyconditioned matrix inversion, which I mentioned, but there's also polyconditioned matrix powering, quantum state testing more recently. All of these are promise problems, okay? So they were sort of asking, okay, is the entry bigger than this number or smaller than this other number, and there has to be some promise gap between these two values. So we don't have that because we can do this rounding essentially, right? We're returning an integer number. Okay, there's some cost that comes with that, which I'll try to explain, but here we are. Okay, what's next? So we tried quite a bit to go beyond what we have here, right? Because it really felt like sort of an initial seed idea. We want to push this further. So what we showed is, for instance, we can sort of relax the constraint, okay? So it suffices that the number of paths leaving S and the number of paths leading to T is polybounded. We don't need this promise on any pair of vertices, okay? And the way we proved it, I think is, I was quite happy with that because it sort of gave us the idea that at least we can sort of get some more leverage out of this idea. So we again consider this counting Laplacian. Now we use a singular value decomposition to write it like that. We pick some threshold kappa, which is going to be 1 over poly, and we split up the inverse of L as follows. right? So we have these sort of small singular values, the ill-conditioned part, and then you have this well-conditioned part, okay? So we can invert this well-conditioned part, but we have issues with inverting this part. So what we do, we just return the effective inverse, okay? We just ignore this part, we're just gonna return this well-conditioned part. Good, so that seems a sort of a fair attempt, but of course, the question now is, like, do we still approximate this number of paths from S to T, right? So does ST entry of L tilde inverse still approximate? Because clearly L tilde inverse is not going to approximate L inverse as a whole, because we're sort of throwing away a very large part of this inverse. However, you can put together two things, namely the two promises that we're imposing. One is that the number of paths from S is polybounded, which implies that this number of paths, you can express it by using the fact that this is a counting Laplacian as the one norm of this thing here. And we know that that is polybounded. Okay, so we know that this thing here is going to be polybounded by our promise. Now that implies, if you look at this singular value decomposition, that somehow the overlap of S with any singular vector with an extremely small singular value should be small, okay? Because we get the sigma j inverse showing up in this expression here. So that means that we have a small overlap with these sort of bad singular vectors. And we can do the same thing for T, okay? So similarly for T, we know that T must have a small overlap with the bad left singular vectors. And it turns out that we need both of these because we can then put these together and we say, okay, if we now take sort of the product of these, we put one sigma j on the other side, then we see that if we put ST around this inverse, right, the relevant entries are going to be terms of this form. All of these forms can be bounded by sigma j times poly n. But by taking the right choice of kappa, we see that the overlap with the small sigma j's can be bounded by 1 over poly n, right? Because we're only talking here about the sigma j smaller than kappa. Okay, so that proves that under this weaker promise, we can still return the number of paths from S to T in quantum log space. Good. So now I want to compare a little bit with what is known. So these classes have been studied classically. So some non-trivial things are known about these classes. Okay, so again, this is our result. One thing that's known is that under just like half the promise, even if the number of paths from S is bounded, then you can solve STCon in log squared over log n space. Okay, so there's kind of a tiny improvement over the trivial log squared bound for general STCon. And that might seem sort of inconsequential, but I think it's quite consequential because it means that, okay, clearly this problem is going to be simpler than general STCon. We don't expect such an improvement for general STCon. Another is that if we still use log squared space, I mentioned Savage's theorem that shows that in log squared space you can solve STCon on general graphs, but the key point is that Savage takes exponential time, okay? So what Lange and others showed is that under this promise, you can solve it in log squared space while still using only poly time, okay? So again, indicates that this problem is slightly simpler than the more general STCon problem. Good. I think I'll wrap up here. So the open questions. So there's this $1,000 reward for dequantization. Okay, so what does that mean? So Eric Allender in 23 got his emeritus, and he wrote this long list of problems that he cares about, that he wants to see solved. One of them is, can you solve STCon on strongly unambiguous graphs? Okay, so that is graphs for which you have the following promise, that the number of paths between any pair of vertices is at most 1. Okay, so if you thought that putting a polybound on the number of paths is sort of making the problem very easy, then you consider this problem. You constrain the number of paths to be at most 1. Can you solve this problem in anything better than this sort of bound that I just mentioned, the log squared over log n? If you can, then you get $1,000 from Eric Allender. That also means that if you can dequantize our algorithm, like put it in BPL, for instance, you can claim this $1,000. Finally, there's two more sort of wider open questions. So we've been trying to prove some sort of BQL hardness for a combinatorial or graph-like problem. Had issues with that, but still, please try. And I think that, to me, like I'm an algorithms person, so what I found most exciting is that we can do something non-trivial with HHL on directed graphs. So both are sort of questions for me, like where can we use HHL and can we do something on directed graphs? Because we don't really understand quantum algorithms on directed graphs. So I'll wrap up here. Thank you.
So I think we can take questions.
Hey, nice talk. So if I understand correctly, you shared the first ever language that's in BQL that's not in BPL, because all the previous ones were promise problems.
Yes.
And is that the one you're trying to prove BQL hardness of? The same language, or?
No, I don't think I expect BQL hardness for that language.
Right. So yeah, I was going to say that because it's a language, wouldn't you expect it's probably contained in some proper subclass of BQL? Because BQL probably shouldn't have complete languages at all. So there should be some some syntactic complexity class inside BQL that actually contains your language, right?
Yes. Yeah, I agree.
Thanks.
Any more questions?
Thank you. What's your expectation for the BQL for your ST connectivity without the promise? Is it going to be in BQL or you expect it not to be?
General STCon?
Yes.
No, I don't expect that to be in BQL. I don't think I have any good reasons not to expect that. I guess that would be an interesting result. No, I don't have anything better to say than that. We tried, obviously we tried. That was the best we could get.
Hi, thanks for the nice talk. I had a very naive question about the Nij and the counting numbers. So I think Nij would usually be the number of walks from I to j.
Oh, right. I'm being a little bit ambiguous here. Yeah,
so you are actually counting walks and not paths, or?
Yes, but I guess maybe they coincide because we're assuming it's an acyclic graph.
But
so
you can have overlap. You can use the same edge multiple times.
Okay, sure.
So basically, we're just considering walks.
Yeah.
Thank you.
That's fair.
So I was wondering if there's any connection between this and quantum walks. Like none of these speedups are actually coming from quantum walks. Do you see there being any?
No, so that's connection? A great question. So one thing that's really puzzling to us is like, what is this algorithm doing? Because it's sort of solving HHL for this, but we would like to understand, like, is it really just doing some sort of quantum walk? Is it doing some sort of Hamiltonian simulation? Because I think that's what we want to understand how quantum walks and things work on directed graphs. We don't. So what you do here is you have to do something, right? You have to double this graph because you cannot invert non-symmetric matrices. You have to double this graph somehow, create like a double cover or something. So that probably gives some insight, but yeah, we weren't able to get anything very useful out of that.
Thanks.
Any more questions?
So did you mention, how did you get a result below else log squared for the classical algorithm for the?
So say again?
For your problem, how did you get below log squared space?
Oh, this is not our algorithm, right? Like,
okay, that's already.
You mean this log squared over log log?
Yeah.
No, this is a result by I think by Allender and
by Allender.
Yeah.
Maybe I can add another question, which is just elaborates on the previous one. So because your algorithm works sort of for this hard instance that was hard for the quantum, for the random walk, this way. So if you would combine the random walk algorithm and your algorithm, perhaps you can cover maybe most of the STCon.
Yeah, that's a good question. So I think like what we've been trying to understand, for instance, if what if you have a lot of paths, so not polybounded, but you also have a lot of paths that go into T, right? Then intuitively, at least a random walk would be able to reach T, but we haven't been able to sort of use that in the quantum settings. So unless you're doing some hybrid, like just running either of the two, I haven't thought of a good way to mix these.